Okay, is this working well? I
Yeah,
had
it
all
looks
these
great.
hopes of making it to the office before my talk, and that's laid plans. So I apologize that you're getting this talk from my kitchen, but still love it. All right, on that happy note, I'm excited to tell you about some of the work that we've been doing in quantum information, quantum algorithms for correlated quantum matter. Sabre pretty much set me up for this talk because I'm going to go into detail in some of the topics that we've been working on in open quantum systems, as well as in QCNNs for characterizing phase transitions in condensed matter. So there's something both for chemists as well as for physicists here, and I hope you'll stay with me throughout this talk. Before I dive into the science, I want to acknowledge this is work by Dr. Kadehed Marsden. I didn't realize she'd be the chair of this session when I wrote this talk, as well as postdocs who've worked with me, Stefan Krasnov, Ian McCormick, who's graduating soon, and collaborators, David Mazziotti and Sabre Kais, again, our previous speaker. So it's a privilege to be here. And if there are any questions, by the way, as I go along, please just ask. I'd hate for us to get to the end of the talk and somebody to have lost the thread early on. Okay, so when we think about predicting the behavior of quantum matter in my group, we try and synthesize across both quantum chemistry and condensed matter. So on the left of this slide, you see methods that you'd recognize from quantum chemistry, where the focus is really on finite systems, where you want to track explicitly the orbitals, you want to think about the potential energy surfaces. You're really interested in observables that would also connect with some form of chemical spectroscopy. On the right of this slide, you see methods that, or I guess observables, as well as approaches that would come more from condensed matter, from materials physics, where we're interested in, say, learning about electronic band structure, learning more about the overall phase diagram, and being able to say something about an extended system. Typically, this is a situation where you can invoke some form of periodicity, and this is that actually gets used a fair bit in the calculations. There's a middle ground here, particularly systems that have become very popular, where you have defects in solids that are acting as qubits, for example, molecular qubits that are not quite as small as some of those finite systems that we're used to, but also not quite extended systems, because again, a defect is something that would break that periodicity. So there is a unique opportunity now to both blend methods across finite and extended system techniques, but also to be able to map some of these calculations onto actual quantum devices. And it's just an area that's really growing. There is a lot of work on the high performance classical computing side, and we do some of that as well. In particular, how can you use GPU accelerated architectures to solve some of these problems? And it's at the moment an open question as to whether these problems, these questions will be addressed using quantum devices better than some of these classical computational platforms, and if so, what is a good apples to apples comparison, right? So I want to acknowledge that there isn't exactly a rigorous way at the moment to, again, say that the calculations that are being done on GPU accelerated architectures can be compared exactly as they are to what's happening on small quantum devices. However, we tend to think of these small quantum devices as providing an additional tool, an additional way of solving some of the same problems that we're independently interested in. Okay, and of course, there is an even more advantageous way to think about this, which is that you could have hybrid quantum classical algorithms. So get the best of both worlds rather than viewing it as a quantum versus classical, combine them to, again, address problems that are independently of interest to the community. So towards thinking about studies of, and there are two parts here. So they're, explicitly, how can we simulate better qubits? And perhaps we can think about solid state qubits and how you could think about an external drive that's coupling these solid state qubits, what kind of learning you can do. Some of those systems themselves look like open quantum systems. And then, of course, there is the algorithms that you can develop for such situations, even if they're not directly applied to qubits. So what do I mean by that? Oh, I'm trying to advance here. There we go. So, some of these solid state qubits, I think, are a nice sandbox for merging some of these same methods in quantum chemistry that we've been talking about, Searle's physics, as well as for quantum information science. So what I mean by that is, unlike traditional, say, transmon superconducting qubits, solid state qubits come in various forms. It's a slightly newer technology. So thinking about these optically addressable spin qubits that are essentially artificial atoms that are trapped in solids. You can think about how these would be coupled. And one way to think about it is that, hey, this is a new qubit platform. Another way to think about it is that, hey, this is an exciting new open quantum system that we want to be able to simulate. In particular, we want to be able to understand, when you start coupling these qubits, they're talking to each other via, say, a bath that is the lattice. Perhaps you have some external control, external drive. You can even think about doing learning on those types of external controls. So I think there's a lot of opportunity here for both algorithmic advances as well as advances that go hand in hand with hardware. Okay, so that's a long-winded introduction to the two very specific things that I'm going to talk about here today. I am getting a unstable internet warning on my end. Hopefully everyone can still hear me just fine today. I'm gonna just out of precaution turn my video off just so that you don't lose me.
Sure.
Okay, but hopefully you can still hear me well enough. Okay, so the two things I want to talk about today, and I really want to go into some detail in these papers that we've recently put out. First, in open quantum systems that are mapped onto quantum devices. These are general open quantum systems. So we're going to talk about a couple of toy models, not necessarily anything nearly as complex as some of the solid state qubits that I showed or some of the big molecules, but how these algorithms are promising towards more complex systems, and how they scale is something I'll address. The second part of my talk, I really want to tell you about some really recent work from our group in branching QCNNs and how these can be used for identifying phase transitions in condensed matter. Okay, so let's get to it. Open quantum systems. So open quantum systems, and this is perhaps a repeat for some of you, especially from Sabray's talk, but these are really ubiquitous in the physical sciences, and anything that talks to the environment, right? So any quantum system that is coupled to the environment, you could think of the environment in two ways. One, that it's a source of decoherence. It's where all the badness occurs. This is what prevents us from having truly large scalable quantum systems. The other is that you could think of the bath as essentially being a resource, and you could think about the bath actually itself having some memory that perhaps you might be able to use. Implicit in that is that you need to somehow be able to describe the fact that the bath has memory, and therein lies that's where the rubber really hits the road. Okay, so there are many classical techniques that have been introduced. Classical techniques here meaning techniques that run on classical devices to especially go beyond the Markov approximation. So, and there are techniques that exist from Redfield, Lindblad. These are the most common mass equations that are invoked. They're certainly not the only ones. And it was recently pointed out to me that there might be historical reasons why these were picked. Perhaps there are better formalisms, but we're going to restrict ourselves to thinking about the Lindblad equation, which is in the form shown here, derived within the Born-Markov approximation. So our first term here is giving us closed evolution. Okay, that's all well and good. And the summation gives us the Lindbladians, with the gammas being the decay rate, and our CKs represent the different Lindbladian channels. Of course, we have our nice anti-commutator. Now, this approach in its present form, especially the classical version, has been applied to a whole bunch of systems of interest, systems in quantum optics, even in light harvesting complexes, cases where you can think about energy transfer that is somehow mediated by the environment, by the bath. My list of names here is not extensive. So if somebody's been excluded, that is unintentional, and I preemptively apologize for that. So by the way, one of the benefits of this equation is that it's derived from Krauss maps, and therefore we are guaranteed, we preserve the positivity and physical nature of the density matrices. And this is a point that will come up again and again as we think about OQS methods. How do we actually guarantee the positivity of the density matrix? How do we make sure that the system is not giving us a result that is unphysical? It's very easy to get something that is unphysical, and of course that's not something that we will want. So when we go beyond, when we start thinking about systems that are non-Markovian, a very natural question is, well, what does it mean to be non-Markovian? And actually, I'll just say, colloquially, you'd say that there is a backflow of either energy or information from the environment back into the system, the system of interest. But more formally, actually defining what is non-Markovian, what is the extent of non-Markovianity is in itself a field of study. Okay, and this is not something that I'll touch on here today, but I just want to emphasize that figuring out exactly what makes something non-Markovian is in itself an exciting question. Okay, so with various approaches that we have, you could think about this generalized master equation that can capture non-Markovian dynamics, but it's challenging for practical implementation, primarily because of that positivity of the density matrix. Preserving that is difficult for some conventional methods. I haven't listed those methods here because that's not really the point. What I want to state is that the method that has actually been developed by Cadet, the ensemble of Lindbladian trajectories, is remarkably good at both preserving the positivity of the density matrix and actually being something that overcomes those previous challenges associated with generalized master equation approaches. And it has an added advantage, since this is a session on quantum computing, that we can actually map it explicitly onto a quantum device. In this context, the quantum devices that I'm referring to are superconducting qubits, especially the devices that we've been able to run on are devices made available graciously by IBM. Of course, in the second part of my talk, where I talk about BQCNN, I'll tell you about some of the work on trapped ion devices. Okay, so this ELT approach, I encourage you to look at some of those references. It's been derived by taking essentially an ensemble over multiple Lindbladian trajectories, and that's in part something that we leverage in mapping this onto a quantum device as well. So the simplest case that we wanted to look at is, and this is, everyone in quantum optics loves the Jaynes-Cummings model. So this is Jaynes-Cummings model in the strong coupling regime. On the left, we show a case that is on resonance, and on right, where we are off resonance. And the classical weights for ELT here, the ensemble of Lindbladian trajectories, were found with numerical optimization to the exact solution. Okay. And this is before somebody asks, it's a common question we get is, where did you get those weights? How do you optimize for them? And how do you know that numerical optimization is in fact the best you can do? Those are all great questions that we are working to address. Okay, so this is, the fact that we can get the Jaynes-Cummings model, strong coupling regime. Of course, this is a system where doing something exactly is in fact possible. And now we want to think about how we can take the same set of dynamics, and I'm going to show you how mapping this onto a quantum device, in particular IBM's London device, is something that we've been able to do. Same Jaynes-Cummings model in the strong coupling and the detune regime, and what we get there. Okay. Okay, so this is now a two-level system in an amplitude damping channel, and our purple here represents the ground state, and the teal or green, depending on I guess how you see it, is the excited state. So solid lines give us the solution on a classical device. So again, this is important. This is a benchmark problem for us, and the dots are generated with the Qiskit simulator, and the crosses are actually on a real quantum device. Okay. So there, I think, various things you could draw from this. I don't want to dwell on this too much more. We can do simple problems, okay? We can do simple problems that you can solve exactly like the James cavity model. We are now working to actually take this approach and apply it to more complex problems in both in quantum optics, but also in some of those molecular systems that I alluded to early on. And we expect that this approach will actually scale quite well on larger quantum devices. So systems we've looked at so far are, very compact quantum devices. These are less than, at least in the cases we looked at, less than 20 qubit systems. Of course, now larger devices are available, and we anticipate using those to look at non-Markovian dynamics, either with ELTQC or derivatives of this method. Okay, so now I want to switch gears and tell you a little bit about the work that we've done in BQCNNs, in particular, the fact that these BQCNNs have direct relevance in thinking about classifying phases in condensed matter, and tell you, why BQCNN over, say, a simple QCNN. Now, those of you who've been following the QCNN literature, or thinking about it, this might be a little bit of a repetition, but let me just introduce why we're interested in QCNNs. So neural network-based algorithms are interesting in condensed matter. They can learn very complex patterns from high-dimensional data sets. And this is now being leveraged both in classical as well as in quantum convolutional networks for classifying complex long-range patterns, both of entanglement and correlations in many-body systems. We know that keeping track of the full many-body wave function, manipulating it is in fact pretty hard. So this is a way to get around it, especially a way to get around some of the high-dimensional data sets that are generated in condensed matter. Now, so far, using conventional QCNNs, and there's been pioneering work by Lukin and others in this field, small-scale devices can already show some gains in learning tasks on large quantum and of course, very large classical data sets, right? And this is where QCNNs have really started to shine because they can perform a binary classification task on a non-trivial phase of quantum matter. I don't have a picture here of such a phase. It's in fact pretty challenging to visualize. I was looking for something earlier that I could point to and say, this is what this high-dimensional data set would look like. And then it immediately occurred to me, well, if I could visualize it, that right there would be in itself a feat. Okay, so the promise of QCNNs, especially QCNNs that have been developed in the past couple of years, inspired us to think about a generalization of it, a branching quantum convolutional neural network, but one that actually has higher expressibility. Okay, and I'm going to come back to how we quantify this expressibility and why expressibility is important here in a second. But the feature that we wanted to leverage for thinking about such a BQCNN is the fact that you have intermediate measurements, particularly intermediate measurements that you can do on trapped ion devices. Following our first experiments of doing this on a trapped ion device, intermediate measurements on superconducting devices have also become available, including from IBM. At the time when we were doing this work initially, we relied on trapped ion devices. And these intermediate measurements can essentially, be obtained in the pooling layers, determine which set of parameters are then used in the next set of convolutional layers. So the hope is that you can have simultaneously more expressibility as well as you can reduce the circuit depth. Okay, so in the figure that is shown here, our blue boxes denote the parameterized SU4 2-qubit gates. You could use, of course, depending on the problem you have at hand, many qubit parameterized gates. I'm not going to try and get into that complexity here with the time I have. And these green boxes are controlled single qubit SE2 operations. And of course, we have the measurements which constitute the various pooling layers. Now, what's important is that at each pooling layer, the control operations are applied to the qubits that will move to the next layer. And a fraction of the qubits are measured and discarded. In our particular case, it's about 2/3 of them. And the remaining qubits proceed to the next convolutional layer. Okay, so that's what this chart here is showing, and this is a schematic of the type of an L-qubit BQCNN with the pooling layers that you'd have. If there's something you walk away with from this section of the talk, it is that intermediate measurement can make a pretty big difference. In fact, it is key to everything that we're doing here, especially in picking which convolutional layer do we proceed to next. Essentially, which branch is determined by outcomes of the previous pooling layer. Okay, now of course there's you measure 2/3, okay, so 2L/3, and of course there's a choice of 2 raised to 2/3 or 2L/3, depending on if you're looking at the generalized case or not, of convolutional layers that can be applied next. And finding the set of parameters for each of these is, again, where as always in any neural network task, where rubber hits the road. Now, this pattern of convolution, pooling, branching, convolution, essentially we rinse and repeat this until we essentially have a small number of qubits with fully connected layer gates, and then of course we measure these. That part is of course common with any other type of convolutional neural network. Now, the motivation for making use of information that we gain from mid-circuit measurements is to increase the expressibility of a fully parameterized QCNN-like circuit, right? But we want to do this without incurring significant error costs. The word error has come up pretty much. You could essentially have a game around that. But when you think about quantum devices, you really you want to circumvent the error costs that would come in because of the circuit depth and the gate count. So, given an n-qubit parameterized hybrid circuit ansatz, we essentially want the full n-qubit Hilbert space to be accessible for some set of parameters. Now, there are two extremes you could think of here, right? If that helps, again, to visualize why mid-circuit measurement here is working. So a circuit that only consists of single qubit gates will be unable to basically represent a majority of the Hilbert space because it can't generate entanglement from all the from the all-zero product state. So that's one extreme. On the other hand, there's a circuit ansatz that represents an arbitrary state in our Hilbert space, which requires 2n minus 1 parameters. So it's a very high-dimensional circuit ansatz, and it's going to be impractical to use in essentially any scenario beyond a very, very, very small system size. So BQCNNs with this measurement, intermediate measurement, allow you to walk that tightrope between those two extremes. Okay. Oh. All right. So now, of course, what's really going to be important for us is to think about this expressibility component. So how do I actually calculate this expressibility? How do I think about this expressibility? Because our entire claim to fame here is that we're actually looking at a system that is going to be more expressible. And because of that, you should adopt BQCNNs instead of QCNNs. Okay, so we calculate this for a particular parameterized circuit ansatz. We randomly generate many different pairs of parameter sets. We calculate the fidelity, and that's this first expression here. Next, we sample over many random sets of parameters, both for the BQCNN and the standard QCNN. We get a probability distribution. So this is how we're making sure this is an apples to apples comparison. We use the Kullback-Leibler divergence and then look at the sample distributions with the random fidelity distributions here. So that's a long way of saying that we essentially have a mathematically rigorous way of, once we have this KL divergence for the two distributions, we can actually directly compare the expressibility of what's happening here. And what we note is that the expressibility, in our case, we used randomly generated data sets But even if you were doing this with a real data set, if you had access to a very large real quantum data set, you would actually notice that a BQCNN is substantially better than a standard QCNN using this way of thinking about the expressibility. There are other ways to think about the expressibility. And if you have a favorite way that we haven't touched on, please let me know, and we're happy to tell you how BQCNN performs there. All right, so the early work on QCNN, on simple QCNNs, was to look at a phase transition for the Z2 by Z2 symmetry protected state. And this, of course, got a lot of attention. It's work by Iris Kong, Lucan, and others, where they looked at this 1D cluster state and then looked at either going from antiferromagnetic or paramagnetic to insulator phase. So our task is a little bit similar, but it's slightly more complex. So we're looking at the ground states of the Hamiltonian here with open boundary conditions on 4 sites. And our goal here will, of course, be then to show that BQCNN is somehow doing slightly better than a standard QCNN. And that's something that for this particular Hamiltonian we've seen. We've executed this now on a Honeywell device, a small trap time device that they've graciously made available to us. And okay, so what's going on here, right? So we have in this particular Hamiltonian, it's very similar to Z2, except that we have various values of these 2 field strengths, H and G here. So 1/2 of the training data set essentially consists of ground states of 6 we have G set to 0. So we have this field strength set to 0, and our H goes between 0 and pi over 2. And then the other training set consists of essentially the other way around, where we set H to 0 and we allow G to vary between 0 and pi. And when we want to diagnose the phase transition, we use this simple string order parameter. And the expectation value of this order parameter is 1 for the SVT phase and 0 for the trivial phase. Okay, so there's a lot I could say about how we looked at the various training sets here. I think that looking ahead, it would be very useful for us to train and test this BQCNN on larger systems, particularly, like I said, on data sets that are real. And of course, if we can somehow intersect this with tensor network algorithms, that would also be pretty spectacular. So we've done, large data sets that we could generate. So we've been able to look at a 4-qubit BQCNN with over 100 free parameters and a QCNN the same width with 66 parameters. We've done double that as well on the small quantum devices, but that's not nearly as large as some of the data sets that you would be able to access in classical convolutional neural networks. Something I want to point out is that when we execute these on a quantum device, we have the same quantum depth for quantum circuit depth for a standard and a BQCNN, especially with this mid-circuit measurement. And this is important because even though our QCNN has these mid-circuit measurements with an immediate classical feedback, which you would think is a possible source of circuit error or some form of latency, it's not. Actually, a traditional QCNN that's constructed with sufficient circuit depth, which gets the same number of parameters as our BQCNN, would actually get much larger 2-qubit gate error costs for a sufficiently wide circuit. So we're not trading off error here for expressibility is a long way of saying this. There are questions here that come up which are common to most hybrid quantum classical variational algorithms. The so-called barren plateaus problem with what happens if you have cost functions and variational onsets in a large parameter space, it grows. So those same questions would come up here. There's some evidence, not conclusive, but there is some evidence to suggest from our calculations that standard QCNNs can actually avoid this issue. And it would be interesting to see if it's true for BQCNNs and other mid-circuit based hybrid algorithms. That would be actually, I think, a big victory if we could say that those issues of barren plateaus are completely overcome because of the QCNN architecture. But that is something that is yet to be seen. So let me just summarize, and I'm going to take a big leap of faith here and turn my video back on and hope this doesn't die. So the first part of my talk, I told you about some of the work in open quantum systems that are mapped onto quantum devices. This is work that was done by Cadet, collaboration with the groups of David Mazziotti and Sabri Kais. Of course, some of the systems we've looked at so far, Jaynes-Cummings model, very, very toy problem in quantum optics, needs to be extended to thinking about, some of the real world problems. I think there is an opportunity here. I didn't get a chance to talk about this here today, a paper we wrote together with Stefan Krasnov and Liang Zhang on actually how you could do learning on quantum hardware and come up with better control for quantum hardware that uses ideas from open quantum systems, but that's a natural direction to go in. And of course, there are the obvious, make a more complex physical system fit on a larger and larger quantum device. There are open questions in how you would benchmark such problems, and that's something that we're working towards as well. The second part of my talk, I told you about BQCNNs, thinking about this SPT phase transitions. There's a lot to do here, in particular, going beyond a simple SPT Hamiltonian, that a toy problem that we've constructed where we had some inkling that we were going to do well with QCNN. So actually looking at a more general set of phase transitions and other types of applications in condensed matter could be good. And of course, doing this with real data sets would make it more of an apples to apples comparison with other techniques in ML and AI. So with that, I will thank the people who've done the work, Cadet, Stefan, Ian, Anthony, and Connor, as well as collaborations, and happy to take questions. Hopefully I'm okay on time.
Wonderful. Thank you, Priya. You're early on time. You're all good. Thanks for a great talk. Are there any questions from the audience? There's none in the chat, but if no one wants to raise their hand now. I'm in a slightly harder spot to ask questions because some of it is work that I don't have too many questions about. David, do you want to go ahead?
Priya, really beautiful talk there. And I have a quick question just on sort of thinking about Sabri's talk and the restricted Boltzmann machines and then the branching quantum convolutional neural networks. Is there some research to be done to kind of get a sense of what types of problems or what types of Hamiltonians might be more amenable to one scheme or another, or this is something that's probably not known? I don't know, any ideas about?
Absolutely, yeah. That's a great suggestion, David, and something that we'd love to work on is, there are probably problems that do well with the kind of BQCNNs that we can formulate, and probably problems that don't do well. So I've shown one example of a type of Hamiltonian. So I wonder if the RBM approach does better for certain other classes of Hamiltonians. It'd be helpful to also know, to develop physical intuition, which I know is very hard to do with neural networks to begin with, but to develop that kind of physical intuition as to which problem is getting mapped onto which and why. Is it because you have a certain type of correlation that enters the Hamiltonian here and certain that doesn't? I don't have a good answer to that, but that would be a really fun question to address.
Right, that is pretty interesting. I guess one approach might be to try to think of a case where the restricted Boltzmann machine would do extremely well, and then just to see like how that might carry over into, or one case, like a really ideal case for both cases, and then kind of swap it. Yeah, interesting.
Yes, we should we should do this. And I see that Sabri is still here. Yeah, that would be a fun question to go after. Yeah.
Okay, cool.
I think that thinking about such neural network architectures and how they apply to problems in condensed matter, this is like very early days. So lots to do here.
Yeah, thank you, Priya. This is really a wonderful talk. I mean, just for the comment about the physics, we're really trying hard to understand. We thought maybe there is a relation to renormalization group where, I mean, the way we do renormalization group, we start with large number of degrees of freedom, and then you have this systematic way to integrate out the degrees of freedom which are not relevant in a scale that you're trying to do. And it's like, again, very similar to what we do in machine learning. We integrate out the degrees of freedom in the hidden layer.
Right.
But I mean, just to make the right connection, we're still not there. I mean, we're trying hard, but I mean, we know it's somehow related, but so far we don't really know the answer, how to relate it in a way that we understand how machine learning works and what is the physics behind it. So this is why we thought to focus on Boltzmann machine, where this can be related to like a renormalization group, but it's not clear how to do it like in a rigorous way. So yeah, I mean, it's still an open question, but I love your approach. Thank you so much.
Thank you.
I have one extra question from the chat that says you calculated the KL divergence between the Haar measured probability and the fidelity. Could you explain that in more detail?
Right. So this is, one of the ways that you could think about comparing the expressibility of the two types of approaches, the QCNN and BQCNN. It's certainly not the only way to, look at, well, if I have the fidelity distribution from the two, the Haar measures for those, are there other divergences I could look at, other ways of looking at the expressibility? Absolutely. This is just how we chose to formulate it based on how people have looked at QCNNs in the past. So, if you think that there's a different measure that you want us to use for expressibility, please just let me know, because this is, in fact, identifying and establishing expressibility, especially coming from the classical neural network side, that's a field in itself. So, if there's a different measure here that you think is better, please, I'm all ears.
For sure. A follow-up from the same person, and on this slide here is U random.
Yes, that's correct. Yes, yeah. So our sets of parameters here are random, and yes, that's doing this again with a real set of real data set would be different. Yeah.
Awesome. These are both questions from Sang Chul, just as a.
Awesome. Yeah, I wasn't able to see that in the, I can't simultaneously share and see, but just write me a note if there are further questions on the expressibility. I would love to, get more thoughts on other ways of quantifying this.
Wonderful. And we still are a little bit early. So are there any extra questions, or are we?
Wow, that's a first for me. I somehow thought I'm going to only have 25 minutes with 5 minutes of questions. So I worried, but yeah.
No, you were all good. Cool. Well, if there's no more questions, then thank you again, Pri. That was an awesome talk.